One of the prime use cases for Kafka and similar technologies is building an internal data streaming platform. Applications within an enterprise can use such a platform to publish and consume real-time data in an efficient and reliable manner. In this video, I'll break down the key components of a data streaming platform. Each of these components can be implemented in many different ways, but the capabilities of these platforms are rather similar across different organizations, because they solve similar generic problems that every organization that embraces data streaming will eventually face. I hope that by the end you'll have a high-level understanding from what components an example platform is built, what function each component fulfills, and how they all work together. Okay, that was the intro. Let's begin. And we'll start with nothing else but Apache Kafka, our broker that everything else is built around. In the year 2010, LinkedIn was growing at an extreme pace, and the demand on the IT infrastructure of the company was growing as well. They needed to figure out a way to support this demand. Messaging systems that were in use at the time weren't able to handle this scale, which resulted in a decision to design and build a new system for this purpose. The requirements: it needed to be horizontally scalable, optimized for massive throughput and low latency. It also needed to be highly available and resilient. The core functionality of this system would be to allow publishing and consumption of messages that would be stored in a cluster in a durable manner, and only removed after they are no longer needed. This is how Apache Kafka was born. Its creation gave rise to the whole field of data streaming as we know it today. Kafka addressed these requirements with its partitioned log-based architecture. Data is logically allocated to append-only logs, which are called topics. Immutable messages are written to these topics. In order to facilitate horizontal scalability, topics are divided into partitions, which can be processed in parallel. If you want to maintain the order of messages during processing, you need to make sure that the related messages are written to the same partition. When you want to consume these messages, you create a consumer group that is composed of multiple similar consumers. Each partition is assigned to exactly one consumer. If you want to scale up, you can run any number of consumers from 1 up to the number of partitions. Your Kafka cluster will store the last committed offset, which means the number of the last processed message for your consumer group. This interface, the partitioned log, is the key innovation here. Messaging systems available at the time when Kafka was created were confirming each message independently. Storing only the offset of the last processed message allows a lot less traffic, efficient batch consumption, and much less logic on the broker side, which translates to much higher throughput per broker. There's much more to Kafka performance than that, but this was the key change. Nowadays, there are many viable alternatives to using Apache Kafka. From different implementations like Redpanda or Confluent Cora, through native cloud streaming solutions like AWS Kinesis or Google PubSub, to Apache Pulsar, which is designed to be a single platform for both data streaming and messaging. Okay, with the broker function in place, we're able to publish and consume messages efficiently at high volume. Very often, one of the first problems to solve will be integrating our broker with other elements of the infrastructure, like existing databases, cloud object storage, or logging platforms. And you could do this manually every time by writing containerized applications and coding the logic of connecting to both sources, mapping the data, and ensuring data consistency. But this quickly becomes repetitive, and it's just a lot of effort solving generic problems. The technology that addresses this problem is Kafka Connect, a large collection of pluggable components that integrate Kafka with tons of different technologies. Kafka Connect is deployed as a cluster independent of your broker. This is where the connectors are running. While the Kafka cluster is dedicated to storing and serving the data by allowing reads and writes to the topics, Kafka Connect cluster is where the connectors are running, moving data from one end to another. Adding a connector to your cluster requires some declarative code and a deployment. After a connector is deployed, the integration is live and your data is flowing to or flowing from your defined Kafka topic. Kafka Connect allows you to easily and efficiently connect different elements of your architecture with and through your data streaming platform. Want to have your Postgres table mirrored in DynamoDB? No problem, just define a Kafka topic and 2 connectors and you're ready to go. The connectors are also battle tested, so the probability of bugs is much lower than if you were to write the integration code yourself. Of course, simplicity comes at a cost. Sometimes you won't be able to get the exact behavior you want from the connectors. In these cases, you might need to write the integration code yourself or find another technology that solves your problem. Kafka Connect is widely adopted. Sadly, I haven't found any hard data, so I need to resort to anecdotal evidence, but I haven't seen an organization that's using Kafka and isn't using Kafka Connect. It's just a low-hanging fruit that brings a lot of value at a low cost. The next core component of our platform is the Schema registry. When different teams or applications exchange data without defining its structure, you'll run into issues very quickly. Imagine one team changing the name of a field in the message they publish, while another team consuming this message isn't expecting it. Now you have a broken consumer and unprocessed messages start piling up. So you'll need a way to define the structure of data in your data streams. And if you do only that, you'll quickly realize that this structure needs to evolve. Bugs will be detected, new requirements will appear. It would be great if you didn't have to migrate to a new topic every time you need to add a new field to your event. You don't. The solution is a schema registry. It's a separate service that acts as a central hub for managing your data schemas. It offers two core functionalities. First, schema management. You upload and manage your schemas here, and the registry maintains the mapping between these schemas and your Kafka topics. This allows your producers and consumers to make sure they are using the correct schema to serialize and deserialize the messages. Second, schema evolution. Schemas inevitably change. The registry allows you to update them, but only if those changes comply with predefined compatibility rules. This prevents breaking existing consumers. Kafka itself is format agnostic. It's the serializer that uses the schema from the registry to convert your data into a binary format for Kafka. A serialized Avro message consists of a schema ID, stored in the schema registry, and a binary payload. Your consumers use the deserializer and the same schema or a compatible one to read the binary payload. Using a schema registry brings several key benefits. It drastically improves the reliability of your data streams by ensuring consistent data formats. This reduces the operational overhead of coordinating schema changes across different teams. And finally, it enables more robust and sophisticated solutions. With reliable and backward-compatible data streams, you can build things like event sourcing systems with confidence. To recap, we've covered Kafka, Kafka Connect, and Schema Registry. I consider these three the core components of a data streaming platform. But in order to run this platform, we need to take care of provisioning and monitoring as well. We're talking about a lot of components here. Typically, you'll have one or more Terraform repositories integrated with your CI/CD pipelines, and integration with your observability platform. This part of the platform will be developed and used by your platform team, but the setup will differ a lot and fully depend on your enterprise IT architecture. If you're enjoying this video and would like to be notified about future releases, remember to subscribe to our channel. So, with these core components in place, you have a solid foundation for your data streaming platform. Now is a great time to onboard early adopters and gather feedback on their priorities. This early feedback is essential. It helps you understand how to deliver the most value in your specific context. It's usually around this time that you'll start talking about some shared conventions about how the platform will be used. But that's out of scope for today's video. What we'll focus on in the next section is how to extend the platform's capabilities. Developing Kafka applications can sometimes feel like working in the dark. You're publishing messages, setting up consumers, but how do you really know what's going on? How do you quickly check message payloads or see if your consumers are keeping up? Having the right tools will make debugging and testing much easier. That's where a platform UI comes in. Think of it as a window into your Kafka world. A good UI, like AKHQ, connects to your Kafka cluster, Kafka Connect, and Schema Registry, giving developers and even business users clear visibility into the platform's activity. With a UI, developers can easily browse topics, inspect message payloads, and monitor consumer group progress. This makes development much faster and easier. Plus, being able to quickly verify message delivery through a UI is incredibly helpful for testing and communicating with stakeholders. Adding a graphical interface is one of the simplest yet most impactful ways to enhance your platform and boost developer productivity. It's a feature that will be appreciated by many users and can significantly improve the overall development experience. Another powerful capability of a data streaming platform is stream processing. While you can often handle this within your client applications, offering stream processing on the platform itself can be a game changer for certain use cases. There are two main types of stream processing. Stateless processing is the simpler kind. It operates on individual messages like mapping, filtering, or masking data. Think of it as a quick transformation on the fly. Kafka Connect single message transforms are a great example of this. Stateful processing is where things get more interesting. Here, operations need to access and maintain state, like joining two streams or performing time-based aggregations. This opens up a whole new world of possibilities. Stateful stream processing can be performed using many different technologies. Apache Flink is a leading solution, so powerful it deserves its own video. But there are other great options too, like Kafka Streams, Rising Wave or KSQLDB, and many more. Many of these offer a SQL-like syntax, making them accessible to a wider audience. Stateful stream processing is a great fit for a diverse list of use cases, examples of which are real-time data pipelines, event-driven applications, or fraud detection. Now, a quick word of caution. While stateful stream processing is incredibly powerful, it's also more complex and resource-intensive to build and maintain. For many use cases, handling stream processing in your client applications might be the better choice. You should carefully consider the complexity and cost before adding this capability to your platform. So, while Kafka Connect and Schema registry are essential for most organizations using Kafka at scale, stateful stream processing is often added later in the data streaming journey. It's a capability you introduce when your platform team is more established and you've identified clear, high-value use cases. As your data streaming platform becomes more widely adopted within your organization, you'll find that more stakeholders get involved, each with their own needs and requests. This is where governance comes in. It's a broad and constantly evolving area, so we'll focus on some of the most crucial aspects. Controlling who can access your data is absolutely essential. A common approach is to use service accounts for applications, with permissions managed through a system like Terraform. In this example, users request access to specific topics via pull requests, which are then reviewed and approved by an authorized person. After merge, the changes are propagated to the platform by Terraform. This process not only enhances security, but also provides transparency, creating an audit trail of who was granted access and who approved it. Compliance with both external regulations and internal policies is another key aspect of governance. And it's not just about meeting these requirements, it's also about having the infrastructure to prove compliance, often through detailed audit trails. Let's take a popular example: handling personally identifiable information. Many regulations require that PII will be encrypted. One way to achieve this is through field-level encryption, like the solution offered by Confluent Cloud. You can tag sensitive fields in your schemas, for example with a PII tag, and then implement a policy to encrypt any field with that tag. When configured correctly, producers will encrypt the data during serialization and consumers will decrypt it. This ensures that sensitive PII is never stored or transmitted in plain text. This example shows just one compliance policy, but many more are likely in use in your organization, often implemented within the applications using your platform. Since compliance is mandatory, by providing features that support it on the platform level, you can reduce the complexity of client applications, which translates to cost savings and accelerated innovation. As your platform matures, you'll likely need to address other areas of the governance function as well, like data discovery, data lineage, data quality, auditing trail, and data retention. The more mature your platform, the more features supporting governance it will need to incorporate. So there you have it, a look at the key components of a modern data streaming platform. Remember that building a successful platform is a long-term effort. While the beginning will often look similar, after you build the core, it's crucial to support your early adopters, gather feedback about what you already have and what's needed next, and plan your way forward based on that. Keep in mind that this was a curated list of the most important and frequently used components. To keep this video concise, I've skipped some frequently used elements like Mirror Maker or Kafka REST. I also focused primarily on what's already adopted and mature. In the future, I'm planning to cover problems that are closer to the bleeding edge of technology. So if you are interested in that, don't forget to subscribe. Hopefully, this was a clear overview of the capabilities of a modern data streaming platform. If you'd like to give me feedback about this video or suggest a topic for our next one, please leave a comment. Thank you for your time and see you in the next video.